Good afternoon, all. Myself, Ashish Joshi. I'm working as a scientist at Photogrammetric and Remote Sensing Department, IIRS, Dehradun. Today, I will tell you about the basics of SAR data processing. So, in today's lecture, the main topics I will cover the radar and SAR concepts, SAR image formation concepts, and SAR post-processing concepts. So first, before we are going to the synthetic aperture radar, I will explain you the basic radar concepts. So radar transmits the microwave electromagnetic radiations, which is called the pulses, towards a scene through the transmitter. Okay, so this is a radar. It will transmit the pulses. So this is the pulses. Okay, these pulses interacts with the Earth's surface and back scattered towards the radar antenna receiver. So these pulses will interact with the Earth's surface, and after interacting with the Earth's surface, it is back scattered towards the sensor, which is the SAR. And after it is getting to the SAR, it has a receiver actually. So in the receiver, it will catch up the signals. Okay, so it observes the strength, means what is the detection, means detection of the signal, what it has transmitted and what it has received, and the time delay. So it has the because SAR is an active sensor, so it knows actually when it is transmitting and when it is receiving. So it is known by the radar like the time delay. So at what time it is starting and at what time it is ending the pulses. So from this time delay, it will calculate the range. Okay, so this radar is a ranging instrument. So from basic mathematics formula, which is time is equal to distance upon speed, we can calculate the time delay as the distance by speed. So this is electromagnetic radiation. So it will travel with the speed of light. So speed we are replacing with the speed of light, and distance actually it is the r distance, which is called the range. Okay, so this is the range. So it will travel the distance twice. Okay, because it is transmitting the signal, so it will first travel this r distance, and again when it is received, then again r distance. So total distance to travel by it is 2r. So the time delay is given by 2r by c. So from this time delay, because we know this time delay in the sensor, we can derive the range. So how much range we are getting? It is Ct by 2. So range is calculated through the time delay. So this is the very much important concept of the radar, means it can very much precisely calculate the range. Okay, from the time delay, because we know the time, then with the help of the time delay, we can calculate the range. So this is the basic concept of the radar, which is the principle of the ranging. So in the radar, we have the antenna. So antenna is the device that directs the electromagnetic radiation emitted from the transmitter to the desired direction in space. So this is the antenna, which has the two components. One is the transmitter and one is the receiver. With the help of antenna, it will deflect the SAR beam on the Earth's surface. So this is the radar beam. So this radar beam is just like a torch. Okay, this we are using the torch in our daily life. So it like torch has a beam. In the same way, the radar has the beam which is in the microwave region. So it will illuminate the Earth's surface with the radar beam. And this radar beam, it is given by the beam width. This beam width is given by this theta angle. So the theta is given by the k lambda by L, where lambda is the wavelength of the electromagnetic wave. So in the electromagnetic wave, because this radar works in the microwave region, so accordingly this lambda will have the value. and L is the length of the antenna, and K is the constant determined by the shape of the antenna. So this shape can be a rectangular shape, it can be a parabolic shape. So we have different antenna for the radars. So now we will come to the synthetic aperture radar. So synthetic aperture radar, which is called as the SAR, is an imaging radar. So normal radar, we cannot see the images. So it will only give one range and one azimuth angle. So that it will not, we are not getting the image out of it. So for getting from the radar, we are using the synthetic aperture concept in the radar, which is a normal radar and the pulse compression technique. We can generate the high resolution images through the synthetic aperture radar. So what is the SAR? SAR is a side looking radar system which makes a high resolution images of the Earth's surface. It has the continuous strips of the ground surface which are illuminated to one side of the flight direction. So this is the normal geometry. So this is the flight direction. So it will a side looking sensor. So it will look the sensor in one of the direction. Signal is recorded and digital signal processing techniques in the ground are used to focus the image and obtain the high resolution images. The across track direction is called the range and the along track direction is called the azimuth. Okay, so this is a flight direction. So as it is moving and it is recording the pulses. So this is the range direction, and with the movement of this radar, it has formed the azimuth direction. So this is the first pulse, means first electromagnetic radiation, but it has received like second, third, fourth, and fifth. Likewise, it will form the image in the azimuth direction. So we have the image in the both the direction. Okay. So these are some of the geometrical parameters of the SAR. So if this is the point, A is the radar platform, then B is the flight direction. So it is moving in this direction. It is called the flight direction. C is called the nadir point. So this is called the just below the radar on the Earth surface. This is called the nadir point. D is the azimuth. D is the azimuth, means with the motion of the SAR, what the image in the ground it will make. So this direction is called the azimuth. This D direction. And E direction is called the, which is called the across track also. This is called the azimuth direction, range direction. And F is called the swath. So what is the numerical value? If we measure this distance, it is called the swath. What is the metric value and what is the measured value? If we measure this value, then the measured value is called the swath, and this direction is called the range direction. And first point in the near point, it is called the G is called the far range, and H is the near point, which is called the near range. So this is the near range, and G is the far range. I is the slant range. So this, as it is transmitting the signal. So all the SAR processing has been done in the slant plane. So this is called the slant plane, and this I is called the slant range. And J is the radar beam width. So likewise, this J is, we are forming, this J is the radar beam width. And this L is the energy pulses, M is the echoes. So echoes means what is the back scattered pulses. So one pulses is the radar is sending, and some of the pulses are coming back to the radar, which is called the echoes. And theta is the incident angle. What is the incident angle? Which is the, if this is the range direction, this range direction, but it is making with the perpendicular to the surface. So this angle is, this is red line is the perpendicular to the surface. So this angle which is making by the range with the perpendicular surface is called the incidence angle. And beta is the look angle. And this beta is the look angle which is making the range with respect to the nadir. So this is the look angle. So for the flatter surface, this incident angle and this look angle will be the same. Okay. And depression angle is the which is making with the horizon direction in the upward. So this is the depression angle. So mainly in the radar, we will mainly use the incidence angle, look angle, slant range, near range, far range, what is range, azimuth, and these are the basic terminology in the SAR for interpreting any SAR image. Okay. So what is the SAR resolution? So what is the resolution? Resolution is the ability of the sensor to discriminate two objects separately. Like this is a definition, standard definition of the resolution. Resolution is the ability of the sensor to discriminate two objects separately. So SAR has the two resolution. In the optical, we are mostly consider about the only one resolution, but the SAR has the two resolution, which is called in the range direction and in the azimuth direction. So in the range direction, we are called the range resolution, and in the azimuth direction, we have the azimuth resolution. Okay. So as I say, like SAR is an imaging radar. So normal radar actually gives the normal single point only, but with the help of the synthetic aperture technique, we can get the high resolution images. So for an image, we should have a high resolution in both the direction, in the range direction also and in the azimuth direction also. So how to get the fine resolution from the radar? So that fine resolution it is getting in the range direction with the pulse compression technique, and in the azimuth direction it is achieved by using the synthetic aperture combination concept. Then the combination of these two principles enables the high resolution in both the range and azimuth direction. So in SAR, we have two resolution, and we are using these two concepts of the SAR like range resolution and the azimuth resolution. So before going to the deeper concepts of the range and azimuth compression, we will just understand what is the pulse, means what is the electromagnetic wave. So electromagnetic wave has some terminology, which is the wavelength, what is the frequency, what is the pulse width, pulse repeating frequency, pulse repeating interval, and sampling frequency. Okay, so this is an electromagnetic pulse or wave. So what is the difference? What is the wavelength? Wavelength is the distance between two successive trough or two successive crests. Okay, so this is the wavelength. And what is the time duration of this pulse, which is called the pulse duration, or which is also called the pulse width? Okay, what is the time duration of this pulse? And what is the frequency? Frequency is the number of crests that passes a fixed point in a given amount of time. Okay, so how many number of crests if we are seeing this point? So how many crests are passing through this point at particular time? So from this we can have this formula of C is equals to lambda nu, and nu is the frequency, lambda is the wavelength, and C is the speed of light. Another important term is the pulse repeating frequency, which is called the PRF. The number of pulses transmitting per second, means as I am saying, in the radar we are transmitting the pulses. So how many pulses we are transmitting in a 1 second, that is called the pulse repeating frequency. Because for this high resolution images, we have to send many pulses at a time. So that many pulses actually will generate the two-dimension image. So what is the pulse repeating frequency? Means at what interval we are just transmitting these pulses. So that frequency is called the pulse repeating frequency. And what is the PRI? Means pulse repeating interval. It is given by 1 by PRF. Means what is the time between the two pulses? Okay, so this is called the PRI. And next is the sampling frequency. Okay, what is the sampling frequency? The frequency at which pulse is sampled for the conversion of pulse from analog to digital. Okay, so normally the pulses we are seeing like an analog signal only, but for our practical purpose we have to transform this analog signal to the digital signal. So from the analog to digital signal we have to do some digitization. So this digitization we have to do some number of samples we have to make. Okay, so that is called the sampling frequency, means at which frequency we are sampling the this signal. So number of sampling we are as a sampling frequency into the pulse width. Okay, so we how many samples we are getting, like fs into the tau. Okay. So first problem for the synthetic aperture radar is how to get a range resolution. Okay, means we have to have the high resolution images. So we should have the both in the range direction and in the azimuth direction the better resolution. So how to get it? So if we are seeing this diagram, so we can see this is the pulse width, means it is a single pulse, and this is some reception window. Then again second pulse, then there is reception window, and then third pulse, then reception window, and this. So this is a transmitter, and here is the receiver will catch up the signal. And what is the this time between these two pulses is called the pulse repeating interval. Okay. So if we can see in this figure, so you can see this is the two targets T1 and T2. It is observed by the radar having two distances R1 and R2. Okay, so what is the resolution? The resolution is to discriminate the two targets separately, T1 and T2. So what is the condition? If this is the first target observation and this is the second target observation in the receiving window. So this is the first pulse and this is the second pulse. And so in the receiving window, we are getting the echoes of both this target in this receiving window, T1 and T2. Okay. And we know what is the time between this one. It is given by 2R by C from the formula of the time delay. So when this sensor will able to discriminate two targets separately, when this distance 2 by C R2 minus R1, okay, this distance is greater than tau. Okay, so this is the criteria. If the time difference between the two target return echo is greater than the pulse width, then only the sensor will discriminate two targets separately. Okay, so this is the condition. Means if the time difference between these two targets is less than the pulse width of a signal, then only it is able to discriminate two targets separately. So here if we do simple calculation, if these two targets are there and it is a combined echo, it is coming. So how to segregate these two targets separately? The condition is this 2 by C R2 minus R1 should be greater than this tau. Okay. And after rearranging this equation, then we are getting delta R is greater than C tau by 2. Okay. So if we will take this tau is equals to 20 microseconds. Okay. If we will take some tau is equal to 20 microseconds and see we have the normal formula. So from this we can have the from the speed of light C tau by 2 we have this 3000 meter and delta R is should be greater than 3000 meter or 3 kilometer. So what is the separation it is requiring? Means it is able to distinguish the two targets separately if the distance between the two targets is around 3000 meter or 3 kilometer. Okay. So we can say sensor will separate two targets separately if distance between them is greater than 3 kilometer. So but we are getting a very coarse resolution, means we are getting a 3 kilometer resolution, which is very much coarse. Okay, so how to solve this one, means how to get the better resolution. Okay, so this is the formula delta R should be greater than C tau by 2. So improvement of delta R demands the reduction of the T. So if we reduce this T value, then we can get this delta R is lesser. Okay. So if we decrease this tau, then it will reduce the energy in the pulses, then detection of the target will be difficult because the average power will decrease. The average power is given by the transmitted power into the tau into the PR. How much repeating frequency we are transmitting the signal, what is the pulse width and what is the transmitting power. So if we decrease this tau, then this average power will decrease. So the detection process will be lesser. So decrease in the tau will not solve the purpose. So what is the solution? The solution is the linear frequency modulated signal or LFM signal. So LFM is a longer pulse with the varying frequency. So normally in normal radars, what we will use, that is the fixed frequency pulses. But for getting a better range resolution, we will use the linear frequency modulated pulse, which is where the frequency is varying. So here you can see the frequency is almost constant, but here the frequency is changing. So in the middle part you can see that is a lower frequency, and in this part it is a higher frequency. So this linear frequency modulated signal actually can be used for the better range resolution, because we can apply the pulse compression technique to get a better resolution for this linear frequency modulated signal. And in this you can see the bandwidth is given by the delta f, and it is independent of tau. Okay, so the bandwidth is independent of tau, and we can construct the large bandwidth for the getting the better resolution. So this is the actually the how the linear frequency modulated signal will look. This is the real part, and this is the imaginary part, and this is the phase part. And if we will find the difference of this phase, then we can get the frequency. So you can see this frequency is a straight line which is linear in shape. So that's why this chirp or this linear frequency signal is called the linear frequency. Okay, because the frequency is linear in this type of signals. Which if the frequency is varying with the signal, then we are getting the LFM signals. So the next is the what is the pulse compression technique. Pulse compression is actually it is an expanded pulse is transmitted and later compressing it to the desired resolution in the signal processor through the match filtering technique. So what is the match filtering? Actually, if this is a reference signal, and if we have two target, echo means first LFM we are getting from first target, and this, then what we can do, just we have to multiply this signal with the complex conjugate. Okay, the received pulse is multiplied with the complex conjugate of the transmitted pulse in the frequency domain. So if we multiply this one, then you can see a very much sharp function. So this you can see this expanded pulse is now as a very much shorter pulse, and in this way we will get a very much finer details or very much finer range resolution. Okay, so this is a technique which is called the pulse compression technique, which is applied on the linear frequency modulated signals in the SAR to get a better resolution in the range direction. So the better range resolution, how much we are getting, it is getting thus by the formula of C by 2B. Okay, so this is given by C by 2B. Just what we are doing in this formula C tau by T, we are just replacing this T with the bandwidth 1 by B. So now this range resolution is not depending on this tau, but it is depending on the bandwidth. So if the signal bandwidth is like 75 megahertz, then we can get around 2 meter of resolution. And with the 750 megahertz of the bandwidth data, we can get even the 0.2 meter resolution in the range direction. So what we have seen, like 3 kilometer resolution, which we are getting without the LFM, it is reduced to the 0.6 meter resolution with the use of the match filtering or the pulse compression technique. Okay. So this is the part in the range resolution. But the range resolution, we are getting the better resolution with the help of the pulse compression technique. Now, how to get the better resolution in the azimuth direction? Okay, so in the range direction, what we have applied the pulse compression technique to give the better resolution in the range direction for the synthetic aperture radar. Now for the azimuth resolution, normally the azimuth resolution is given by the formula of lambda r by L, which is the lambda is the wavelength, r is the range, and L is the length of the antenna. So just we will calculate how much is the azimuth resolution we will get. So if we will use the r of 800 kilometer, means if we are having the space-bound data from the Earth observation satellite or low Earth orbit, then we have this 800 kilometer, and lambda, because it is working on the microwave region, so we can choose the lambda as a 3 centimeter, and the length of the antenna we can tell as a 12 meter. So if we substitute this formula in this form in this equation, then we are getting around 2 kilometer resolution in the azimuth direction. Okay, so which is very much coarse resolution. So now in the azimuth direction also, with the normal radar we are getting and the azimuth direction and the very much coarser resolution, which is called the around 2 kilometer with this configuration. But in the same configuration in the optical, actually we can get a better resolution, because we have actually in the optical, this is type of formula, theta is given by 1.22 lambda by d, where we will use the lens, but there we will use the lambda as a very much in the visible region, which is in the micrometer. Okay, so with this formula we can get in the optical a very much finer resolution with the lenses and mirrors, but in the microwave region with the antenna we cannot get a very much high resolution in the azimuth direction. So the range direction we can get the higher resolution with the pulse compression technique, but in the azimuth direction still we have to do something to get a better resolution in the azimuth direction. So let us consider how to get a better azimuth resolution. So we will formulate one question: how much antenna length to achieve the azimuth resolution of 0.6 meter? Okay, so from this formula, just we will invert this formula. We can get L is equals to lambda r by rho a, which is the azimuth resolution. Lambda is the wavelength and r is the slant range. So if we can use this lambda, if we can have this 0.6 meter resolution, means if we want the resolution of 0.6 meter, so we can substitute this 0.6 meter, r is 800 kilometer and lambda is 0.03 meter. So how much antenna length it is required? It is now around 40,000 meter or 40 kilometer length. So for getting a better azimuth resolution of 0.6 meter, we should have the 40 kilometer antenna. Okay, so for if we are carrying this 40 kilometer antenna, it is not feasible. So how to create a larger antenna? But the solution we are getting, like if we have the larger antenna, then we can get a better azimuth resolution. Okay, so we cannot make this larger antenna by physical mode in the space. We can make this by the synthetic aperture concept, this larger antenna. So what is the synthetic aperture concept? So synthetic aperture concept is that actually we are simulating a larger antenna with the motion of the SAR. Okay, so as if actually if you can see, this is the radar and this is the target and this is a SAR beam on ground. Okay, so you can see this target is in the SAR beam. Okay, so if we can see when it moves in this direction, so this target it will be remain in this beam. Okay, so this target actually will observe by the multiple position of this SAR antenna or radar antenna. So we can see like for this target it is behaving like a larger antenna. So this actually larger antenna is creating by the motion of the radar. Okay, so this is called the synthetic aperture. Okay, so real aperture is this one, but with the motion of the SAR, the target is in the SAR beam for a particular time. So that is creating a synthetic aperture for this target. Okay, so this azimuth resolution is improved using this synthetic aperture technique, which is with the motion of the SAR we are getting the synthetic aperture. So in this direction also we are creating a LFM actually in the azimuth direction by the motion of the SAR. So this LFM, which is the linear frequency modulated signal, in the range direction we are actually transmitting, but in the azimuth direction this LFM signal is made by the motion of the SAR. So in both the direction, in the range direction also and in the azimuth direction also, we are making the linear frequency modulated signal in both the direction. Okay, so in the azimuth direction we are using the synthetic aperture concept to create this LFM signal. So this is actually the synthetic aperture concept. So as you can see, this target is seen by the multiple positions of the radar, and you can see this all this position actually the SAR signal is coherently added, and the synthetic aperture length is given by the formula 2 lambda r by L. So how much synthetic aperture length it is created by the geometry? It is given by the 2 lambda r by L. So if we will substitute these values like 3 centimeter, 800 and L, so how much length of synthetic and length we can get? Around 4 kilometer. If we can have 3 centimeter of wavelength, R is of 800 kilometer, and this normal real aperture is the 12 meter. Okay, so from this, how much synthetic aperture length we can get? We can get a 4 kilometer this synthetic aperture length. So if we can calculate now improved azimuth resolution by the formula of R into azimuth beam width, which is lambda by L. Now this L we can substitute as L by S, this LS. So this LS, if we will substitute here, so how much antenna azimuth resolution we are getting? It is around L by 2. Okay, so for a normal phase, we can get a azimuth resolution of L by 2. Okay, L by 2 means if the real aperture is of 6 meter, then from the synthetic aperture we can get the azimuth resolution of 3 meter. And if it is of 12 meter length antenna, then improved azimuth resolution is of 6 meter. Okay, so these are two basic techniques in the range and azimuth direction to get a final resolution in the SAR images. Okay, so main things you have to remember: the LFM is a longer pulse with varying frequency. High resolution in SAR images is achieved by the pulse compression and synthetic aperture concept. The SAR range resolution depends on the pulse bandwidth, which is given by the C by 2B. SAR azimuth resolution depend on the antenna length, which is called the L by 2. So in the range resolution, it is depend on the pulse bandwidth, and in the azimuth resolution, it depends on the antenna length. And the radar azimuth bandwidth is given by lambda by L, and azimuth resolution is given by the lambda r by L. So these are some of the basic formulas for calculating the resolution in the case of SAR. So by using this concept of the pulse compression in the both in the range and azimuth direction, so we can focus the image. So this is the SAR raw image. Okay, so like optical case, we can have a feeling of some features in the image, but in case of the SAR, we cannot have any feature in the raw image. So you cannot see any feature, just we can see this type of, this is called the real part of the raw data. So as the SAR has the complex data, so we have both the channels, real channel also and the imaginary part also. So this pulse compression technique is applied in the both in the range and azimuth direction to focus this data. So this is called the raw data, and after doing the SAR raw data processing, we can get a focused data. Okay, so this is the basic steps or basics concept of the SAR image formation. Means we have to know about what is the pulse compression, linear frequency modulated signals, and what is the synthetic aperture concepts. So this is called the raw data, and this is called the process data. Still this data has some geometric issues. It is not proper. Further, we have to do the processing. Okay, so after that, I will tell you about the post-processing. This is the normal raw data level processing, how the first image is formed from the raw data. So this is the SAR raw data, in which we can see, and this is the SAR real component and SAR imaginary component, and we can derive the amplitude by the square root of real square plus imaginary square, and the phase is given by the tan inverse of imaginary by real. So in the every pixel of the SAR image consists of the real and an imaginary part, which contains the amplitude and the phase information. So what are the different SAR data products? We have the raw data product, which is called the signal level data. Okay, we can have the slant range product or process product. In this, we have the single loop complex product SLC, and we have the SLD, which is called the detected product, which is the amplitude product. After that, we have to do some geometrical corrections. Then it is called the ground range product, and after that, geocoded products. So geocoded products are also the two types. This is called the geocoded ellipsoid corrected product and geocoded terrain corrected product. So this is the basic signal level data we have to process into slant range product. But the slant range product still has the geometrical issues, so we have to correct this. So by converting into the ground range and by converting into the geocoded products. So here you can see this is the raw data. This is a signal processing technique, which is called the pulse compression techniques and match filtering techniques. We are applying and we are converting into the single look complex data. This is the process data. And after doing this, we have to do the post processing. We can convert into the ground range product. We can convert into the geocoded ellipsoid corrected product, or we can convert into the geocoded terrain corrected product. Okay. So what is the slant range product? Actually, the slant range SAR can image both in ascending node and descending node. SAR can look in the both right and left direction because SAR is an active sensor. So it can actually both of them. Most of the optical imaging in the India, it is actually in the descending mode, but due to the SAR, it can be no botheration of the sun, so it can image on the night also. So in both passes we can have the data in the descending mode data also and in the ascending node also, and it can look in the right direction also, in the left direction also. Okay, so in this slant range product we have the flipping. Okay, so it can be flipped in the range direction or azimuth direction, and it is not geometrically corrected. Okay, so we have the some of the features which is actually in the SLC product. It can have some flipping in the azimuth direction, in the vertical direction, or in the range direction, which is called the horizontal direction. So if we can see this range and azimuth, if this is the actual area, actual Earth surface, so if it is in the ascending right mode, okay, means ascending means it is going this one and it is seen in this direction. So you can see it will image this area first, and it will write this area as here. Okay, so in this way you can see there is a flipping in the azimuth direction as it is moving in the ascending and right. And second is ascending and left. If it is moving here and it is looking as a left direction. So you can see this area is image first, then it is writing this image, this feature here. Okay, so this is called the ascending left. In the descending left, it is the descending left. So in this direction, it is going and it is seeing in this direction. So it is the proper geometry we are getting. So as the Earth surface, then we are getting the proper geometry. And in the ascending left, we can have the like it is sorry, descending right. If we have this direction here and right direction is here, then you can see we have observed this this is first. So you can see in this image this features are coming first. So you can see in the slant range products there is a flipping in the range and azimuth direction due to the looking in the both in the range direction and azimuth direction. So this is not geometrically corrected. Okay, so we have to do some geometrical corrections like geocoding and geocode terrain correction for viewing the products in a proper geometry. Okay, so in the slant range product, the pixel direction is in the range. Okay, so and the scan direction is the azimuth. And we in the slant range process product, we have the single loop complex files, which is called the SLC, where we have the two files, real and imaginary. Okay, so if we have the SLC data, when you anything if you want to do, then we can have the two files in the SLC. One is the real and imaginary. So this SLC data is very much useful for the actually for the different application like polarimetry application and the interferometric application. This phase information, because from the SLC data we can get a phase information. So it is very much useful in the actually in the polarimetric application and the interferometric application. And this is the detected image, means if we want to visualize the data. So what we will take, we just take the amplitude. So this is the single image. Okay, and it is geotag, means that is the in the image it has the lat long information. Okay, the image is not rotated. Okay, you can see it is in the this geometry only, in this direction only. Only the we can have the geotagging, means if just lat long information we can tag it with the help of the SAR geolocation techniques, which I will cover in the next slide. Okay, and what is the range pixel size in the slant range products? Actually, it is given by the C by 2fs range pixel size. What is the range, means in an image? What is the pixel size it will give? It is given by the C by 2fs. Fs is the sampling frequency. C is the speed of light. Okay, so in the slant range product, we don't have the square pixel size. Okay, so it has the somewhat compression is there. Okay, so range pixel size same and azimuth pixel size changes with the mode. So you can see the slant range data. So you can see this is the real part data. This is the imaginary part data. So these are the two images in the processed image. And if we can take the amplitude, if we can just take the square root and real square plus imaginary square, then we can visualize this image, which is called the single look detected image. Okay, and after that, actually since actually you can see I have already told, like, this is not in square pixel size in the slant range. So you can see this in the slant range geometry, the features are slightly compressed. So this is called the slant range image. So as the data is acquired by the SAR in the slant range plane, so it is processed, but it is not actually geometrically corrected. Okay. So the SAR image can be presented in either in the slant range or the ground range. So many of the SAR satellites, either they will provide in the SLC data or they can provide the ground range data also. So it is your need or your basic application what you want to do. So if you want to do any polarimetric and interferometric application, then you have to go to the SLC data. And if you want to just for the object detection or visualization, anything you want to do, then you can go for the ground range data directly, and you can just do the further post processing to get any useful information for the from the products. And here actually in this, as I am saying, like in the SAR slant range, the geometry is not corrected. So what we have to do, and we have to do the ground range correction. So you can see after doing the ground range correction, now the pixels have the proper square size. Okay, and it is now at the proper features are properly. Okay, so how to convert this slant range into ground range? It is can be done through this formula. So if this is the SAR and this is called the slant range, all the SAR data acquisition will be done in this slant range plane, and this is called the ground range. This is actually on the ground we have to project the data. So this is the theta, which is called the look angle. And for the flatter surface, this theta angle is equals to this incident angle. Okay, and from this geometry we can find out the relationship between the slant range and the ground range, which is coming out as a ground range is equals to the slant range by sine theta. So in the image, if we know the look angle or incident angle, then we can just convert that data from the slant range to the ground range. Okay, so with the help of the theta or the look angle, we can just convert the slant range image to the ground range image and the pixel in the square size. Okay. Now, what is the SAR geolocation? So, this is the actually the slant range product. This is called the ground range product. Now, still actually this data is not in the geographical coordinate system. Okay, so for using this data and to compare this data with the other satellite products, like with the optical data or with the hyperspectral data or the multispectral data, or we have to use in the GIS environment. So we have to have some geographical information, or we have to have this geographical lat long. So actually in the SAR or in optical, we don't directly get this lat long information for any pixel. So SAR geolocation or geolocation is the calculation of the geographical coordinates of the image pixel. Radar measures the range from the sensor to target. Okay. Okay, so already I have told you about the range. And the synthetic aperture radar actually additionally measure the Doppler history of all the returns target. Okay, so because actually it is, as I am saying, like in the synthetic aperture concept, so it has the actually with the help of the motion of the SAR, it is making the synthetic aperture. So with this motion, actually there is a relative motion between the earth and the sensor also, or the target and the sensor also. Then it will have the Doppler effect with the respect to relative motion. So it will also give one more point parameter which is called the Doppler. So we have one Doppler parameter and the range parameter. So with the help of these two parameters, we can make a one sensor model which is called the rigorous sensor model to geolocate the pixel position on the ground. Okay, and we don't need any roll pitch yaw information for the geolocation, because we can estimate this roll pitch yaw through the Doppler actually directly. So in the unlike in the case of the optical, we need the exterior orientation like roll, pitch and yaw to geolocate any target in the optical images. But in case of SAR, because we are estimating the Doppler directly from the image, so we don't need to have the roll, pitch, yaw angle of a sensor satellite to geolocate any target. Actual Doppler is estimated from the image needed for the SAR image focusing. Attitude information essential for the optical sensor geolocation, and it will depend on the attitude accuracy. So in the case of the optical sensor, we should have the geolocation with the respect of the roll pitch yaw. So roll pitch yaw in that onboard may have some inaccuracies. So optical sensor may have some geolocation accuracies due to this attitude accuracies. But in case of SAR, if we are able to focus the SAR image, then we can have very much precise geolocation, because we have the precise range information and precise Doppler information. So with the help of the range and Doppler equation, we can have the precise geolocation. So what is the geolocation? Geolocation is the process of the calculation of the geographical coordinate, which is called the latitude and longitude of a image pixel. Okay, so you can see if we want to geolocate any target, so this is the SAR image and this is the enlarged view. So for a particular target, what is the latitude and longitude? So how we can get it? So it is done through the three equations. One is called the SAR range equation. Second is called the SAR Doppler equation. And third is called the Earth model equation. Means Earth is a spheroid or ellipsoid. Then with the help of the ellipsoid equation and the range equation and the Doppler equation, and we can calculate the this unknown x, y, z. So if this is a SAR sensor, we know this R and we know the satellite position, means we know this time, what is the time, what is the positional value, and what is the velocity of this SAR sensors. So with the help of this R and these parameters and with the Earth model equation, we can construct a simple SAR rigorous sensor model to geolocate any target. So in SAR geolocation, what basic concept we have to follow? First, we have to assign for a particular scan pixel. For a normal in an image, we have the scan pixel. So for a particular scan pixel, what is the latitude? So that is called the image to ground geolocation, or we call the forward geolocation. So for a particular IJ, what is the lat long? So this is called a forward geolocation. Okay, this we have to do. And second is the backward geolocation we can do. What is the backward geolocation? So for a backward geolocation, actually for a particular lat long in the geographical plane, we have to find out where, at what scan and pixel from the SAR slant range image it is coming. Okay, so if we have any digital elevation model, so for that digital elevation model, we have the latitude, longitude, and height. So what we want to do for that latitude, longitude, and height, where in the SAR sensor it is giving the location of the IJ. So that is called a backward geolocation. So for a particular lat long to IJ. So basically in SAR geolocation, we have to do these two types of geolocation from image to ground and ground to image. Okay, if we are able to do these two type of models, then we can do the geometrical corrections in the SAR image. So SAR geocoding actually is the process of resampling the slant range image from the SAR coordinate system to the geographical coordinate system. Okay, it means first actually if we are seeing in this image, so this is in the slant range image only. So first process is to first we have to find out the latitude and longitude for a particular pixel. Now, after knowing this ij, we know this ij, we have this lat long information. Now, we have to rotate this image in the geographical coordinate system. Okay, so we have to resample the data in the geographical coordinate system. So that is called the SAR geocoding. Okay, so this geographical coordinate system pixels are computed through SAR geolocation algorithm, and after computing, we have to resample the data in the geographical coordinate system. So this process is called the SAR geocoding. Okay, now this SAR geocoding we can have in two ways. First, we can consider the height of the scene as a constant, and an average height we can give like a smooth ellipsoid for a particular satellite image. So when a surface is considered as a smooth ellipsoid surfaces, then we can have an average height, and we can do the geocoded ellipsoid correction, which is called the GEC, where the actually if we want the surface is flat, or where the dams are not available, like in the ocean regions, deep oceans where the dams are not available, then just we can create these geocoded ellipsoid corrected products for the proper geographical coordinate system, because this data is not towards the true north. Okay, so it is in the sensor geometry data. This is a range direction and this is the azimuth direction. But we have not resampled the data in the proper map geometry. So we can do by two ways. First, we can consider by considering the smooth ellipsoid, and if the dam is not available. Second way to consider the digital elevation model. Okay, so it generates the precision corrected product by the use of digital elevation model, and it is create the ortho rectified images. So we can overlay the SAR images with other optical images or anything other GIS products. So you can see here this values we have to have the X, Y, and Z. So Z component actually it is given for the height actually. So that height actually for the terrain X, Y, Z, it is given through the digital elevation model. So for a particular point, we can have the latitude and longitude. But if we have the digital elevation model, or we can have the Z value also, then we can create a very much precise products. Okay, so that precise products are called the GTC or ortho rectified products. And this is called the geocoded ellipsoid corrections, which is having the height, average height. And if we are using the dam, this is called the precise terrain corrected products. So in this you can see this is the raw data. Okay, so you can see no processing has been applied, and it as from the data signal level data we can get. Okay, so this is no feature we are able to do, but by doing the signal level processing, by using the match filtering in the frequency domain in the both in the range and azimuth direction, we can able to focus this data. Okay, so mostly the space agency give this type of SLC data. Okay, and for the research point of view, if anybody wants the raw data to do their algorithm to do any comparisons or make a better products, we can use the raw data product also, but we should have the understanding of the SAS raw data processing or signal level processing. So if we mostly they will give the SLC data or the ground range data. Okay, so if we want to do the further research, we can directly use the raw from the raw data itself. We can ask and we can do the processing. So in this raw data, nothing is visible. In the SLC data, it is the focus product in the range direction and azimuth direction. We have the using the pulse compression technique. We have able to focus the data. Here, focusing is not there. And still in the slant range products, what I have told you, it has geometrically not corrected because it is having the not the square pixel size, okay, because it has the C by 2FS, and we have the compressed images, and moreover due to the ascending and descending and left and right, it has the some flipping in the range and azimuth direction. So it is not geometrically corrected or not towards the true north. So what we have to do, we have to do some post processing and to do the some geometrical corrections. So these are the two geometrical corrections we can do. First, we can do in the form of the ellipsoid correction where we will have the height information, and second we can do in the form of the terrain corrections where we can use the dam information. So you can see this is the general without any dam we have just do the we have done the and geocoded ellipsoid correction, and this is the geocoded image. So you can see this is the raw data, this is detected image, and this is the rotated image. So this is the rotated image means it is the rotated towards true north. So this is the proper geometry. So here you can see here the actually ocean is coming in the left side, but actually it is on the right side. So by doing the this geolocation geocoding procedures or post processing procedures, we have correctly geometrically corrected the data. Okay. So this is the basics data processing concepts. Okay, means what we have understood, how the image SAR image has formed, what are the challenges in the range and azimuth direction, how it can be solved, what is the solution. Solution is the linear frequency modulation, and the pulse compression technique in the range direction, azimuth direction. We have to do the synthetic aperture concept. After focusing also still there is a geometrical issues, so we have to do further processing of geolocation and geocoding to get the proper product. So this is the final. If you can use the digital elevation model, then you can have the ortho rectified product. So that ortho rectified product is the final product which can be used for the any, or we can compare this data with any other optical satellite data or hyperspectral data or any other data. Okay. So this is all in the my lecture, which is covering the SAR data processing, which is covering the basic image formation concept, which is called the raw data processing, and the post processing technique, which is called the level 1 data processing. Okay. So if you have any doubts, you can post the doubts in the chat box, and I will answer you after few minutes.